Hello. So today, let's continue our discussion on the improvement in the policies in reinforcement learning problems. Okay. So the improvement in the policies is very important in RL. This is simply because that if we have some policy that is fixed for all time, and that is not helpful, right? Because we have a fixed policy, then our agent cannot learn any useful knowledge and to make better decisions in a sequential decision making problem, right? So here we want to show this argument and to also not only the intuition of the proof but also the rigorous mathematical proof for this argument here, okay, which is called the monotonic improvement of the policies. Okay, so with this improvement, then we can make sure that the policy that we going to rely on in the RL algorithms, it will be useful, or we can use those policies to learn something, right? Okay, so and later you will see that this is also very useful in calculating the temporal difference errors and even the fundamental of Q-learning and also the base of the DQN, where we need to compute the target Q values in DQN. Okay, and we know that DQN is almost the fundamental of all the modern RL algorithms, right? So now we can see that the importance of the this mathematical result of this improvement of the policies. Okay, so why we're calling this as the monotonic improvement, this is simply because that for all the state, for all the S here, we want to have this result. Okay, so where this is simply represented as below in this box. So we're saying that the value function, okay, you can refer to the previous videos for the value functions or Q functions talking about the expected rewards. So the value function is given the state S. So we use this pi I in the superscript to denote this this old policy value. Okay, so let's just write a notation. So this will be the old policy value. Okay, and this would be the new one. Okay, we say that for all the states, and this old policy value is less than or equal to the value under the new policy. Okay, given some state S for all the states. Okay, so by the definition, so we say that this is a new, so it simply means that if we're gonna use this pi I plus 1, it will be just notation for, or definition here is such that we have this argmax by choosing some A, which maximize this Q function, okay, under this pi I, given S and A. Okay, all right, so that's the idea, that's the statement of this monotonic improvement of the policy. So here I simply write several sentences to help us to further understand the intuition, the basic intuition of this proof before the mathematical proof of that. Okay, so we say that by choosing some action A, okay, or some action at each time step, so we can maximize the current Q or the future Q values, and then we can expand this current Q using all the future Q values. Okay, or we can expand or nest that Q using the notation in rewards, the discounted sum of future rewards, right? So where at each time step in the future, then we can always, again, by choosing some future action to maximize that future Q value, right? So we don't have to worry about future. So at each time step in the future, we can always, by choosing this argmax, by choosing some A or A prime or A double prime to try to maximize this future Q, okay? But be careful that all those future Q values, they are having the same superscript of this pi I, okay? So it means that each Q, no matter it's current or future, it is just improved from the original policy pi I, okay? So in brackets here, I said that every future q is improved from pi I to pi I plus 1. Okay, so that's it. We do not have pi I plus 2 or pi I plus 3. Okay, we just improve once. Okay, no matter it is next time step or it's the third or fourth or the last time step, we always expand the or nest the future q value into the form of future sum of future real words, but in terms of only we still have the maximization by choosing some future actions to maximize the future q, but that would be the q with the same superscript of pi I. Okay, and later you will see the mathematical proof. And during the nesting, we always improve from the v pi I. Okay, so no matter it's the s, the state is s or s prime or s double prime in the future, so on and so forth, but they are all based on pi I. When we can always improve once from pi I to pi I plus 1, no matter which time step we are. Okay, good. So finally, then after all those nesting or all those improvements, then we can finally get what we can finally get is simply this pi I plus 1, just one little improvement ahead. And that'll be giving us this value that is greater than or equal to the current policy. Okay. All right, good. So now let's try to write some mathematical proof. This proof is everywhere. You can find this everywhere on any textbook. But here, let's try to follow this proof and verify our intuition of this proof. Okay, good. All right, so let's start this. So the value of the old policy's value, v pi I given some s, not equal. So this has to be less than or equal to if we choose some action A to maximize the corresponding Q value. Okay, so there's no big difference between the V and Q for the current, but it's just Q takes two arguments S and A. Okay, so we were saying that this is the V is less than or equal to the maximization of this Q by choosing some A. This is simply because that they are essentially the same. Okay, but by choosing some action A, where we can reach the maximum of those things. Okay, so by choosing the maximum, then this has to be greater than or equal to just some normal values, right? Which is not maximized on the left hand side. Okay, good. So and as we said, let's use the format of the real words to the sum of future expected real word to discounted future real words to rewrite this Q value. Okay, so that'll be the max over this A and the reward, the immediate reward R as A, okay, plus gamma, good, and so this would be the discount factor, the gamma times the summation of some S prime state. Okay, so now we have our Markov transition probability, PS prime S A, okay. So that would be nesting the V pi I, okay, S prime. Okay, if you are not familiar with this, then you can refer to the Bellman equation or the previous videos, and this is not difficult. Okay, so this would be just a very regular or normal expression to using the sum of future real words to represent the current Q. Okay, here, okay, importantly, this would be S prime. Okay, if it's S, then this is wrong. Okay, S prime. Good. All right. So, by the definition of this maximization over A, okay, so this A, it has to be something. Okay, we have already written this here. Okay, so we have this. So let's just read this again here to make sure that we do not forget pi I plus 1 as, so some new policy, okay, that'll be just defined as the argmax if you choose some A to maximize this Q pi I of SA. Okay, good. So by definition, okay, So we can rewrite this as, so we can just remove this max, right? And then we change this a to this pi I plus 1. Now we have this specific value for this a. Okay, so plus gamma and summation s prime in s, and the same p s prime s. And again, this a is replaced, right, by pi I plus 1 s. And the same thing else. Okay, this is by the definition of pi plus 1 in this step. Okay, all right. So that is not the end of the world, right? So what is the end of the world? That'll be, we need to further expand this. Okay, so this is just x single prime. We need to expand that to x double prime and all the way to the end. Okay, so how do we do that? And that'll be just a repetition of the first step, right? Exactly. So this would be just smaller than, less than, or equal to the same thing for the first term. Okay, plus n gamma summation s prime p s prime pi I plus 1 s. So we can simply replace this v using the q, right? And by taking the maximization, that would be greater than or equal to the thing above. But here, be careful, we're choosing some new action a prime because we're under the state s prime. So that would be the maximization of q pi I s prime, a prime. Okay, let's put this in the bracket. Good. So this step is simply because this is less than or equal to this. Okay? All right, let's just add some color to those things so that you can distinguish the differences. So this is less than or equal to this. And that is exactly the same logic in the first step. Okay? All right. Good. So what do we do next? And then next will be just a repetition of the second first step, right? So that'll be just the repetition of this inequality here. So that'll be just using the reward to expand or to rewrite this max q under over some a prime, right? So we copy and paste the first and second term. The first term is s pi I plus 1 s plus gamma summation at p here s prime s pi I plus 1 s, and then multiplied. Okay, so here is a multiplication multiplied by, okay, so we can just further expand or further nest this q with some reward function, right, with the format in the reward and then the future state. Okay, so again, as we use in the above steps here, you can write this as r s prime pi I plus 1 s prime. Okay, so here be careful, we have all those s primes, plus gamma times summation. This would be s double prime because we're taking one more step further, and this would be the p s double prime conditional s single prime pi I plus 1 s single prime, and here it'll be v pi I s double prime. So here you can see that although we change all those s to s primes to s double prime, but here eventually in the expansion here that we nest for all those q values using the reward formats. But here be careful that in all those value functions in the superscript we always have this to be pi I in the end, in the last bracket. Okay. All right. So, and now you know next what to do for next, right? And so on and so forth. So, finally, you can imagine that. So what we're doing here is to try to expand all those those Q functions in the format of those future discounted future real words, and using the V pi I, but replacing the S to S single prime to S double primes. So so eventually we'll exhaust all those states for all the time step, but we can see that, okay, so something very important here that we can observe is that we only have pi I plus 1, okay, no matter how far we go from here, okay. So eventually then you realize that what we can get is this value function under pi I plus 1. So eventually we just made one step ahead by changing, by picking or by choosing some optimal action under each time step for each state in the future or in the current. No matter what time step is, we simply choose some action to maximize that, that Q value. Okay, but be careful that no matter how many steps we have, we simply improve from the previous pi to a new pi, which is pi I plus 1. Okay, there will be only one improvement. Okay, but this one improvement, that is already enough for us to show that this V, given some state, any state actually, is V pi I, that will be always less than or equal to this V pi I plus 1. Okay, so that means if I take some action, okay, and also in encoding later, you will see that we simply need to, by choosing some action A, to try to maximize this Q function. And that'll be enough for us to guarantee or to make sure that the policy will be improved monotonically for all the states. Okay, good. So, and that'll be the mathematical proof and also the intuition and the implication for this improvement of the policy that we're going to use almost all the time, right, in reinforcement learning problems. And that'll be useful for calculating the temporal difference, the errors, and the target Q values in Q learning, in DQN, deep Q network, and almost any algorithms in RL based on those fundamental things. Okay, good.